Hello everyone, I am Mihira Lakruwan. I am from National Building Research Organization Sri Lanka. Currently I am studying at Tohoku University, Japan. My topic is evaluation of the performance of landslide mitigation measures at Ginigahthena. This is a part of my research I have done for my master's degree at University of Moratuwa, Sri Lanka. My supervisor was Professor Kulathilaka. There are many steep cut slopes in Sri Lanka's road network, mainly in the central region of the country. And there are many requirements to cut into those slopes for road widening. Such road widening on Avisaville and Nuvaraliya Road reactivated an ancient landslide at a bridge in Ginigahthena area. Considering the importance of this location, the Ginigahthena landslide was mitigated using drainage improvement techniques and soil nailing. In this study, I am going to evaluate the performance of those mitigation measures. This is the landslide location. This is a S.A.D road and the bridge. So the requirement was to widen this bridge. For that, excavation was done in this close to this bridge pier. So by this excavation, the top support of this ancient landslide was removed. The landslide was reactivated. The important feature is there was a marshy land on top of this landslide, always waterlogged area. Due to this, the water table profile in this area was very high. So our objectives are to evaluate the effectiveness of different mitigation measures on slope stability and emphasize the importance of stage construction and following the top-down approach and following the correct sequence in landslide mitigation works. So first, we did an investigation to find the slope geometry and the subsoil profile. From this one, we developed two numerical models to simulate the slope for seepage analysis and slope stability analysis. Then those models were validated using the monitoring data and the investigation data. Then using the seepage analysis, we found the pore water pressure for different drainage improvement techniques. And this pore water pressure values we taken as input to the stability analysis and find the factor of safety values. This is the 1 meter into a contour map we obtained from the topographical survey. This is the bridge here, and this is the landslide boundary. And we have advanced 3 boreholes along the central axis of this landslide. And this is the borehole profile we obtained. The bottom we observe rock layer and then residual layer. And top of the landslide, we observe the loose soil layer. Then we design mitigation measures considering 3 main aspects that's surface drains, subsurface drains, and soil nailing. So these are the surface drains we applied the plan view. On top of the landslide, we applied a cutoff drain, and landslide body we construct berm drains. And important thing is in the marshland, we applied or constructed this kind of surface drains. The top part is a regular surface drain, which collect the rainwater and runoff. And below this regular surface drain, we install a trench drain. This trench drain will collect the drain out the water in this marshy area and lower the groundwater table at the crest of the slope. Then as subsurface drains, we install 20 meter long horizontal drains, and as soil nails, we install 16 meter, 12 meter, and 8 meter soil nails. So this is the existing or the original slope profile before mitigation. Then it was excavated in this profile to allocate the 10 meter road widening at the top. So this excavation was done in 3 construction stages like this 1, 2, and 3. So we're going to evaluate the stability of each construction stage for different mitigation conditions. So to do that, we consider a design rainfall event, which has a 300 millimeters per day peak rainfall for 2 days and at 50 followed by a 50 millimeters per day residual rainfall. This is our analysis matrix. So as I said, we have 2 drainage mitigation measures as surface drains and subsurface drains. So we consider 3 drainage conditions as no drains, only surface drains, and surface and subsurface drains. As soil nails, in soil nailing, we consider no nailing and nailing conditions, and the 3 construction stages as I discussed in previous slide. So altogether, we have 18 number of stability analysis. We did it for calculated the analysis for in every day for this design rainfall event. So this is the variation of the factor of safety at construction stage 3, or the final factor of safety values with the design rainfall event, the daily variation of the factor of safety. Top brown color lines are corresponding to the slope with soil nails for different drainage conditions, and bottom blue color lines are corresponding to the slope without soil nails for different drainage conditions. So we can see that this here there are two lines in each condition. There are two lines close to each other. Those are for the no drains and only surface drains conditions. So when we apply subsurface drains, we can see that we were able to increase the factor of safety significantly. So the factor of safety of the slope without any mitigation measure is after the excavation is about 0.8. By applying the soil nails and surface and subsurface drains, we were able to enhance it up to the 1.5. So this is the vector safety variation at construction stage 1 and 2. But I'm not going to into detail here. But important thing is the minimum factor of safety values are obtained usually at the end of the peak rainfall event, or at the day number 7. So this is the variation of the minimum factor of safety values at each stage for different conditions. As similar to the previous slides, the top brown color lines are corresponding to the without nail conditions for different drainage measures, and bottom blue color lines are corresponding to the without nails with different drainage conditions. So here we define two target factor of safety values. To maintain the short-term stability, we need a factor of safety of 1.1. To maintain the long-term stability, we need factor of safety of 1.3. So if we consider stage 1 excavation, we only have to maintain the short-term stability, so we can apply soil nail with any drainage condition. But when we go to the stage 2, we have to apply soil nail with either of drainage condition. So when we go to the stage 3, we have to maintain the long-term stability condition. So we have to apply soil nails with both surface and subsurface drains. So here, the point is, if we do the excavation of stage 2 without applying the mitigation measures of stage 1, slope is at a risk of failure. Similarly, if we do the excavation for the stage 3 without applying both the mitigation measures for stage 1 and 2, slope is at a risk of failure. So it is important. So it is important to follow the to do the stage construction following the top-down approach. The other point is, as I said, the water table profile was high in this area. So when we do the drilling for soil nails, the soil nails drill holes are tend to collapse, and water was collected on those drill soil nail holes. So when it was difficult to do the grouting for soil nails. So what we did was, before applying the soil nails, we constructed the horizontal drains and lower the groundwater table. By doing that, we were able to overcome that problem. So it is important to follow the correct construction sequence. Considering all those, we applied all the nailing and drainage measures at each stage. So we follow this path in our construction. So now I come to the conclusion. The ancient landslide at the Ginigahthena was reactivated due to toe excavation for road widening, and it was stabilized using extensive mitigation measures. And drainage improvement can enhance the stability of the slope, and subsurface drainage are more important. In this site, soil nailing was mandatory to achieve the stability requirement. And in soil nailing, stage construction following top-down approach and adopting construction sequence is important to maintain the failure during the construction. And also drainage measures can helps to overcome the potential construction problem in soil nailing. That is the end of my presentation. Thank you very much for your attention.